Okay, have a quiz. First problem was to write out the quadratic formula. About half the class did. And the half that didn't, make sure you know the quadratic formula next time, okay? And you'll be glad that you did, especially when you get your pre-calculus class, when you get into quadratic functions, which probably come out pretty soon for some of it, okay? Within a couple of weeks for everybody. Which equations are quadratic? Well, that's a linear equation, okay? It's a linear equation of two variables, actually, x and y. Okay. This one is quadratic because what's the test for quadratic? Okay. Test is going to be put into the form if it be put into this form, it's quadratic. If it isn't, if it can't, it isn't. Well, how would you put this into the form of a quadratic? I'm going to pause the video for a second, see if you can answer that. Okay, well, the key to the question is, what's unique about this form? And what's unique about this form is it has that equal to 0 there, right? And this doesn't have equal to 0, but if we subtract 3 from both sides, we can set this equal to 0. Okay? So this is quadratic. And I'll make a little note here. Subtract 3 from both sides. Okay? This is no not quadratic. If I multiply both sides by x, which I have to do to put this in any kind of form like this, because there's no x in the denominator here, is there? We can have an x in the denominator. Besides, anytime you have an equation with a denominator, you multiply by common denominator, okay? You got one denominator, you multiply by that. If you got multiple denominators, you find a common denominator and multiply by it. Very important, and people generally have a difficult time getting that through their heads, okay? So I gotta keep talking about it. We multiply both sides by x, and of course that would give us an x cubed there, wouldn't it? Okay. So put that kind of small, it just says multiply by x, we're going to get an x cubed here, and this doesn't have an x cubed in it, right? So trying quadratic. Now this one is a little ambiguous. We could write this as x squared minus 2x minus 3y equals 0. Okay. And if you regard your 3y as a constant, you could actually put this into the quadratic formula, right? Okay. So we'll say maybe not, depending on how we want to interpret it. We won't actually have to deal with these, but I'll put it in there anyway. A little questionable how you want to define your terms. Well, let's go on to using the quadratic formula. So we have x squared plus 5x plus 6 equals 0. So this is a form ax squared plus bx plus c equals 0, with a equal to 1, b equal to 5, c equal to 6. Right? So all we have to do is write out the quadratic formula. Here's the formula. X equals negative b, which is negative 5, plus or minus square root of 5 squared, minus 4 times a, which is 1, times c, which is 6, 2 times 1. So I just plug the numbers in for a, b, and c, and that's very easy to do if you know the formula and if you know how to recognize a quadratic, okay? So, yeah, we could have done the same thing with this equation once we subtract the 3 from both sides, okay? We'd have had a equals 3, b equals 5, c equals negative 3. And we'd put those numbers in and see what we get. Very simple. First, let me do the arithmetic. Get negative 5 plus or minus the square root of 1 over 2. Find the square root of 1. Well, 4 times 1 times 6 is 24. So you have 25, which is the square of 5, minus 24, which is 1. So everybody's going to get that. I'm not concerned. You all can do your arithmetic. Okay. Yeah, do it carefully. Okay, so x equals, this is plus or minus. Okay. So you have an or here. So x equals x equals negative 5 plus 1 over 2, which comes out negative 2, or x equals negative 5 minus 1 over 2 equals negative 3. Those are your solutions. Now, I'll say just a little more about this. This means if you want to graph x squared plus 5x plus 6, because this is going to come up in the next assignment, okay? The graph of let's say y equals 0. Well, if x squared plus 5x plus 6 equals 0, right? Zero if x is negative 2 or x equals negative 3. Then, if you have a graph, and you have, let's say, negative 2 here, and negative 3 here, and of course, there'd be negative 1, there'd be 1, 2, and the scale is terrible. There. Okay. Then, this point's on the graph, and this point's on the graph. Okay. Now, another thing we can find is what's the y-intercept of this function? Okay. Well, let's have a quick discussion here. Okay, so how do we find a y-intercept? Well, I said, well, how would you find a y-intercept of a linear equation? Well, somebody said, okay, linear equation of y equals mx plus b, right? So you know you're going to get a straight line if you graph it. Well, your straight line is going to have slope m. Okay. What's the y-intercept going to be? It's going to be b. Why is that? The y-intercept occurs on the y-axis. Now, what do you know about x if a point is on the y-axis? What do all the points on the y-axis have in common? So what's the x-coordinate of, you pick a point on the y-axis, what's the x-coordinate? It's 0. Any point in the y-axis has an x-coordinate of 0, right? Because any point in the y-axis lies above or below x equals 0. So this is something you're going to need real quick. So y-intercept it's a point that's number 1 on the graph of the function. Number 2 is on the y-axis. Okay. On the y-axis implies that x equals 0. Okay, it's actually if and only if statement. If it's on the y-axis, x has to be 0 because it's directly above or below x equals 0. The x-coordinate of every one of these points is 0. And of course, if the x-coordinate is 0, that is going to be on the y-axis. So it's an if and only if statement. You kind of throw that idea away, but let's move on. So if x is 0, you're going to have 0 squared plus 5 times 0 plus 6. And what's 0 squared plus 5 times 0 plus 6? It's 6. Yeah. So this point is 0, 6. At this stage, then we know that this graph is not a straight line, is it? Okay. It can't be a straight line. Well, the graph of any quadratic function, any function y equals ax squared plus bx plus c, is a parabola. Got this shape, or upside down. Okay. So got like up or down, and it's nice and symmetric, and we'll talk about that a little more in a minute. Okay. So can I draw a nice parabola through these points? Well, I'm going to ask you to sketch my picture here. You don't have to copy all my words, just sketch my picture and see if you can draw a parabola that fits those 3 points. I'm not expecting miracles. You know, drawing an accurate parabola is kind of tricky. Okay, but you should be able to make some kind of an attempt. Haven't, but you'll see. Okay. Okay, well, about half the class got a nice looking parabola. None usually pretty good look. Okay. Gonna have to come down here. Down here. Go through these points. Then come back up here. And just be nice and symmetric. So you can have a what we call the axis of symmetry here. goes halfway between the zeros because it's going to be symmetric on both sides, right? So what's on this side should be a reflection of what's on this side. I didn't do that well. You know, this point's that far on the right. Yeah, actually, I didn't do that badly, but it's a little close on this side, okay? So I didn't do a great parabola, but that's kind of the way it looks. And at least half of you drew nice parabola, good looking parabola, okay? Probably better than mine. Okay. So that's pretty good. Since we're doing this, give you a little terminology. This vertical line here is your axis of symmetry. This point down here is called your vertex. Okay. And I'm going to let you in on the secret already. The secret is the axis of symmetry is halfway between your zeros, right? No, it's not hard to understand, at least historically. I find that people have a little bit of trouble understanding it, but what number is halfway between -5 plus 1 and -5 minus 1? Show me with your fingers if you can answer that. What's halfway between -5 plus 1 and -5 minus 1? Okay. Yeah. I think this -5. Okay. I mean, on the graph, yeah, if you're to graph just this numerator, -5 plus 1 is -4. -5 minus 1 is -6. What's halfway between -4 and -6? Well, what's halfway between 4 and 6? 5. So halfway between -4 and -6 is -5. Yeah. Okay. That's not hard to understand. Well, halfway between -b plus the square root and -b minus the square root. Well, let's discuss that for a minute. It's hard to indicate that with your fingers of one hand. Okay, well, questions, what's halfway between -b plus the square root and -b minus the square root? Well, the square root is going to have the same size for the plus as the minus. It's not going to change, right? So if you've got a number line and -b is here, okay? And -b plus the square root is here, then where's -b minus the square root? Well, it's the same distance on the other side, right? So what's halfway between what's on this side and what's on this side? Yes. Does that make sense? So halfway between -b plus the square root and -b minus the square root is -b. So what's halfway between -b plus the square root all divided by 2a and -b minus the square root divided by 2a? Well, a little further than I really need to, but I'm just going to say it and then we'll write it out more thoroughly, or I've got room to write it out. You could write this as -b over 2a plus or minus the square root over 2a, right? So halfway between -b over 2a plus the square root over 2a and -b minus the square root over 2a is -b over 2a. Right there is where your axis of symmetry is. The axis of symmetry is that x equals negative b over 2a. And it's halfway between the zeros. Okay? And the vertex is on the axis of symmetry. So if you want to know the y-coordinate of the vertex, you just plug the x-coordinate into the equation and you get it. So the quadratic formula not only tells you how to solve a quadratic equation, we can see it. It tells you how to find the vertex. It tells you first how to find the axis of symmetry. Once you know the axis of symmetry, you know what to plug into the equation to get the y-coordinate. You know the coordinate of these two coordinates of these points. Okay. Now that's kind of a big chunk of understanding that I thought I'd talk about it right now. First time we actually solved an equation. Well, not the first time because we did it last time, but okay. So this is, as I say, it's a big chunk of stuff because, well, we'll see a little more. I don't want to go that far yet. Okay. Now let's take the other equation, which is x squared plus 5x plus 7 equals 0. Plug into the quadratic formula. It's just like this, except we're going to have a 7 or we have a 6 here, because this equation is the same as this, but I changed the 6 to a 7. Now, this throws you a little bit of a curveball because 4 times 7 is 28. So 5 squared is 25 minus 28 is negative 3. Okay? And square root of negative 3 is not a real number. There's no number that you can square and get a negative. Your number would either be positive or negative. Well, if you square a positive number, you get a positive number. If you square a negative number, you get a positive number. There's no number that can be squared to give you a negative. So the square root of a negative is not any real number. Well, we're going to write this up. This is negative 5 plus or minus the square root of 3 times the square root of negative 1. Because 3 times negative 1 is negative 3. And the square root is just an exponent, so it distributes over multiplication. We'll see that. We haven't really dealt with the laws of exponents. But take my word for it, that works. Okay? Now, what's the square root of negative 1? It's not a real number. Okay? We call the square root of negative 1 I for imaginary. We have real numbers and we have imaginary numbers. Now you might think, no, that's absurd. That's not a real number. What good is it? Well, you know, it would still be most likely driving horses and carriages if it wasn't for imaginary numbers. We certainly wouldn't have nuclear power, which has advantages and disadvantages. We wouldn't, well, much of our modern technology requires imaginary numbers. We ought to figure out how to make good bridges. drive our horses and carriages on. You might even figure out how to make engines, but the mathematics you have to do to design a really good engine requires complex numbers, which require imaginary numbers, okay? And your solution here is a complex number. So we call this, of course, you're not gonna understand how all that works out. Just take my word for it. In higher level mathematics and engineering, you just can't get by without it, okay? Complications get way, the calculations get way too complicated. -5 plus or minus the square of 3i over 2. Which I can write like this. Okay. Now, what are the implications for the graph? Well, the graph has no zeros. When I say a graph has no zeros, also it has no points on the x-axis. Okay. No points on the x-axis. Now, can you draw me a parabola that has no points on the x-axis? Sketch me a set of coordinate axes and sketch me a parabola that doesn't go through the x-axis. Okay, so I've seen a variety of solutions. One is that parabola would be above the x-axis, okay? So it never hits the x-axis, just keeps on going up, right? Now, if you draw one down here like this, and stop it here and here, that doesn't mean the parabola actually stops. You've just restricted the domain of the parabola, which is an important thing to understand, okay? Which is why I'm going to mention it. You know, the parabola goes on. So, you know, it's kind of like you got arrows on it. You probably see arrows on these things in the open map. And the arrows aren't a bad idea, but this thing continues, and if it continues getting steeper and steeper. So you don't know that necessarily about parabola, okay? So drawing that would be a very plausible answer to the question, okay? It stopped before it got to the x-axis, so it didn't go through. That's until you realize that, well, the equation of this thing has a value for any value of x, no matter what x is. So if you make x quite a bit bigger, you're going to get something on the other side of the x-axis, okay? So this would be a yes. This would be a no, but it wasn't a bad idea. And the other way, only one person did this. You draw one below the x-axis, it has to turn down, right? Okay. So if it's below the x-axis and turns up, it's going to go through the x-axis. If it's above the x-axis and turns down, it's got to go through the x-axis because it goes on forever. It keeps getting steeper and steeper. Okay, so these are two ways. Now, what we have here is no points on the x-axis, right? But what do we know? Okay, so well, what's the axis of symmetry and what's the y-intercept? say, well, can you draw me a set of coordinate axes and show me where the y-intercept of this graph would be? How do you get the y-intercept? It occurs when x equals 0, right? Something you got to really understand. Because it's always important to find the y-intercept of any graph. And you can always do that very easily by substituting x equals 0 in the equation. Okay? You can also find the x-intercepts by substituting y equals 0. If we substitute y equals 0, we get our quadratic equation, right? And this tells us that this graph doesn't go through the x-axis because you don't have a real solution. It's not a real number. So it's either above or below the x-axis. You'll be able to determine whether it's above or below by figuring out what the y-intercept is. So what is the y-intercept? Okay, so you're having trouble finding the y-intercept, and I said a couple of times, read this. So let's go back over what we said here, make sure everybody understands. Y-intercept is the point on the graph that's on the y-axis, right? If it's on the y-axis, then x is 0. If x is 0, you figure out what y is, and that's your y-intercept, right? Okay. So it comes out, but you need to understand that logic, otherwise you won't remember. Okay, if you shortcut that by just saying, well, it's going to be C, and never understand why it's C, then there are other things about graphs that you're never going to understand. Okay, or that you're not going to understand well when you first encounter them. Okay, very important to understand that the y-intercept occurs when x is 0 because the points on the y-axis are exactly the points where x equals 0. And you have to understand that about graphs in order to understand graphs. You can't get very far until you work that idea out. Okay, so we've got to make sure we work that idea out. Nevertheless, that tells us that the point 0, 7 is on your graph. Okay, well, there are a lot of ways to draw a parabola through the point 0, 7 without intersecting the x-axis, right? You know, maybe the parabola is like this, maybe like this. Okay. Until you know what the axis of symmetry is, because you notice that the axis of symmetry of this one is here, and the axis of symmetry of this one is here. Okay, to get a better picture, and really to get a good picture of your parabola, you need to know the axis of symmetry. Well, which is it if it's either one? Okay, it's going to look something like one of these. It's not going to be down because that would end up going through the x-axis. Let's go back to the axis of symmetry. I said x equals negative b over 2a for the same reason it was before. Except that reason doesn't really hold because you don't have real zeros to go halfway between, right? But you can still think of negative b over 2a as being halfway between negative b over 2a plus the square root over 2a and negative b over 2a minus the square root of b over 2a, even though the square root's not a real number. Okay, you can't represent it in 2 dimensions, and you don't want to go to the 4-dimensional representation because that's really tough. Okay, way beyond the scope of what we can do. You know, actually, any time in the first 2 years, even if you're an engineer or mathematician. Okay. So, axis of symmetry is here, and that's at still negative 5 halves, because that's only determined by the A and the B. The C has nothing to do with where the axis of symmetry is, because it's at this over this. Okay. At negative B over 2A, at negative B over 2A. Whether this is real or not, that's where your axis of symmetry is, and that's something you want to lock in. Because if you do, something that's pretty tough that you're going to encounter very soon in true calculus becomes much easier to understand. That's what we're trying to prepare in this course. Okay. So that's negative 5 halves. So, okay, well, let's put negative 5 halves here. Okay, well, the axis of symmetry of this one's about here, so it's not quite like this shape, but it's going to be kind of close. We got to go through here, and we got to go through here. Now, what we don't know is how high or low to go. But we do know that the graph might be like so, or like so, or even like so. Okay. These are all possibilities. To determine which one, you have to plug negative 5 halves into the equation. Well, I'm going to kind of leave it at that for the moment. Actually, here's the close, so I don't want to necessarily leave it at that. I don't need to date my head here for a second. Okay, I'm going to do it. Even though I'm out of board space. Okay, so what am I going to do about that? Well, get another board. Say, I don't always cooperate. Okay, let's see here. Okay, we're good. Okay, so now, what do we know about this? Now this is x squared plus 5x plus 7. Y equals x squared plus 5x plus 7. We know that the y-intercept is 0, 7. We know that we get that by plugging in x equals 0 because the point on the y-axis has x coordinate 0. So if we plug in 0 here, we get a point on the graph when x equals 0, and that's our y-intercept. So there's a point on our parabola. Now, if we understand that the axis of symmetry and that doesn't even depend on, well, it does depend on that. It depends just on the 5 and the 1 in front of x squared, right? Value of a and b, negative b over 2a is negative 5 halves. So we have a point on the axis of symmetry. So the x coordinate's negative 5 halves. We plug in x equals negative 5 halves. I'm going to ask you to do this. Plug in x equals negative 5 halves. Show me then where that point is going to be. The point for x equals negative 5 halves.
Recording progress.
So we have a little trouble getting started. We want to find the point on the graph of this function when x equals negative 5 halves. The point on this line, x equals negative 5 halves. Okay. That satisfies this. So where are we going to plug in x equals negative 5 halves? I'm going to plug it in here. I'm going to get a y coordinate, right? So we want to plug in negative 5 halves for x up here and evaluate it. Everybody can do, not everybody solve where to plug in. Okay. So you want to understand why we're doing that. We're trying to find the graph of this function, trying to represent the graph of this function. So we find the point on the graph when x equals 0, that's our y-intercept. We use the negative b over 2a to find our axis of symmetry. And then we plug that number in for x to find the y-coordinate, and then we have a point on the axis of symmetry, right? Okay. We want to understand the logic of that. We want to understand that that's what we're doing and why we're doing it, okay? Okay. The idea is then we plug in x equals negative 5 halves. So y, and we plug it in to the equation of the function so that we get a point on the graph of the function. So we get y equals negative 5 halves squared plus 5 times negative 5 halves plus 7. And I'm not going to go with arithmetic of this. You can't get the arithmetic of these fractions. There are a couple of assignments in fractions, one multiplying fractions, one adding, subtracting fractions we do last week, right? You really have to be straight on fractions because soon we're going to be doing rational functions, and you use all the rules for adding and multiplying fractions when you do that, but it's not just with numbers. So if you're not good on those rules, you're going to have trouble. So make sure you know how to work with fractions. So 5 times negative 5 halves is negative 25 halves. 5 halves squared is 25 over 4. You got 25 fourths and negative 25 halves, okay, which gives you 25, negative 25 fourths. And you add that to 7, and you get 6 and 4. 25 fourths. Yeah, you got 3 fourths. Now I'm going to put a question mark. I did that in my head. I didn't write it out. I was thinking I was going to get 1/4. But I don't see where I messed up. Let me just double check myself. You have negative 25 plus 50 is, you're going to have 25 minus 50, which is negative 25, plus 28. That's going to give you 3. Okay, it's 3/4. My intuition went haywire there. I was going to be closer to 0 than that. Anyhow, it's here. So this is the point. Negative 5 halves, 3/4. Now, if this is 7, you know, we could put 8 maybe about here, so that 4 would be here, and 2 would be here, and here, and 1 would be about here. So it's plausible that that's a little less than 1/3. So that's not too bad. Okay. Now make sure you understand how to do that. And preferably understand why. And first understand the steps, they're pretty simple. Okay. You find the axis of symmetry using the negative b over 2a. The reason for that is to find it It works whether your solution is complex or real. The quadratic formula. And that gives you your axis of symmetry, and then you plug whatever you get on the axis of symmetry. You plug the x coordinate, the axis of symmetry into the function, and you get the y coordinate because the y equals this, equals this. And now you have a point on the graph. And what do you know about that point? That's the vertex, the low point of your parabola. So if you take this picture and don't take time, because I'm not going to give you time to line off a complicated x and a y axis, just draw a picture. Picture might be this here, and then an axis of symmetry and a point down here. Just sketch me a parabola through this point and this point, where this point is the vertex, the extreme point, the low point, or if the parabola was upside down, which it isn't, it would be the high point of your parabola. And that's very important for applications and other things. Okay. What this tells us, well, here's the picture. It comes down here, it levels off, and it comes back up. Not great. It's a little too flat at the bottom. Wasn't my best parabola. Okay. But it gets the idea. And it's not really symmetric. It's too wide on that side. So it really kind of sucks, but that's okay. Okay. Now, here's the payoff. We can sketch the basic function, which you should understand and should know how to sketch. And you can have an assignment on this. So here's your basic one function. Okay. Now, if we shift y equals x squared left, a 5/2 of a unit, that is -5/2 in the horizontal direction. -5/2 is over here. If there's -2, here's -3, and here's -5/2. If we shift this thing over here, its axis of symmetry was the y-axis. Its axis of symmetry is now -5/2, right? Okay, so we get a graph that looks like this. Okay, so this is y equals x plus 5/2 squared. So that's what a horizontal shift does. Okay, transformation, stacking first chapter. Okay. Then we shift it up 3/4 of a unit. So it's going to shift every point up 3/4 of a unit. This point's gonna go up to here, and this point's gonna go up to here. You got a point over here that'll go up to here. And you're gonna get a parabola. It looks like this. It's gonna have an axis of symmetry. So x equals -5/2. Its equation is this. Okay. Well, if you expand x plus 5/2 correctly using distributive law and add 3/4, here's your x squared plus 5x plus 7, which is the equation we have. So that this equation, you get the horizontal shift by figuring out the axis of symmetry. You just take your basic y equals x squared parabola and shift it right or left to the axis of symmetry and write out what the equation would be using the rules. And then you raise it or lower it if necessary. Okay. And you raise it or lower it by figuring out what the y coordinate is. Now we plug your x into here, and that tells you how far you raise or lower. In this case, it's 3/4 of the unit. Now, if you get all that sorted out, you're in really good shape to get into graphs of polynomials and all this stuff. And what's chapter 3 and the Lippmann text, I'm not sure where that occurs. And the Larson text, I think, is the other section of pre-calculus is using. But it's coming up in both courses, and it looks pretty much the same in both courses, okay? So hopefully that's going to do you some good.